All right, so hello everyone. I'm here with Luke Barnes. Luke is a lecturer in physics at Western Sydney University in Australia. He works on cosmology, galaxy formation, and the fine-tuning of the universe for life, and is one of the world-leading experts on fine-tuning. Luke also is quite good at philosophy, which is very rare among physicists. Usually physicists sort of dismissively sneer at philosophy and then make an ass of themselves when they talk about philosophy. But so it's rare for a physicist to actually understand the philosophy, and it's sort of nice and refreshing. So Luke, thanks for coming on.
Yeah, thanks for having me.
So in your view, so first, just for people who are unfamiliar with the fine-tuning argument, do you want to just lay out sort of like what the basic argument is in a nutshell?
The basic argument is, starting about 5 decades ago, really, physicists were looking at these things called the fundamental constants of nature. So within our equations, there are numbers that we have to put into the equations, as opposed to numbers you get out of the equations. Those are the predictions. But those numbers you've got to put in, those are the fundamental constants. Things like, the mass of an electron. How heavy are electrons? And it started about 5 decades ago. Physicists started to do something that we do with all free parameters in our models. A fairly standard thing when you're a physicist is to say, well, what if they'd been different? What if these numbers had been something else? And what was noticed was that while everything was mathematically fine, if you started changing these numbers, you ended up with a physically very different universe. A lot of the time, there are a lot of cases where a small change in some of these numbers would produce a dramatic change in the universe towards simplicity. So, for example, things just wouldn't stick together. The sort of bonds that are holding us together and the Earth together and all that sort of stuff just fail, and the universe won't stick together. And this was called the fine-tuning of the universe for life. You've just got to get these numbers in a fairly small region if you want the universe to do the sort of things that we think any sort of life would need. And so this was, widely discussed. If you're a theist, this looks like design. This looks like, well, obviously, there's something amazing going on around here in terms of life. And that has followed us all the way to the bottom of physics. And so it's not surprising that you have to do something pretty amazing to have a universe that permits life. Our universe did it because God worked it out, and there's no reason why a naturalistic universe would do it. So that seems like a score a point for God.
Yeah, as I think it's important what you note, which is that a common objection that people raise to fine-tuning is they'll say, well, maybe life could have arisen under different conditions. But people can only think this if they're not at all acquainted with the physics of the actual fine-tuning, where the idea is that no two atoms stick together. It's not like, well, maybe you could have had, silicon-based life. If no two atoms stick together or things immediately implode, there's no life is going to arise, certainly. So, in your view, what are kind of the most impressive kinds of fine-tuning? What are some of the parameters that are set in particularly precise and improbable values that, in particularly improbable ways, give rise to the formation of life?
So I think the best cases are as follows. There's a number called the cosmological constant. So in 1998, we discovered that the expansion of the universe is accelerating. So it's not just getting bigger, it's getting bigger faster and faster. So there's a number in our models that represents that. And what we can do is say, okay, what if that number had been different? There's a mechanism that might be behind it that involves quantum fields, the way the stuff of the universe is put together, and the question of whether there's any sort of energy in empty space, even when there's no particles. The fields are there might still be energy. If there is, that would behave like a cosmological constant. But regardless of what the mechanism is, we can say, look, let's explore other ways the universe could have been by changing this number. And we find that over the range that it could have had, that's consistent with the model, there's an extraordinarily small range that allows for the existence of any kind of cosmic structure. So just as you were saying, you know, these changes, you don't stick to anything together. Unless this cosmological constant is extremely small compared to the scale it could have had, you know, no two particles touch each other in the history of the universe. It's that sort of outcome that's on the cards. So if you want a number, there's the sort of range that this number could have in our models. It goes out to something called the Planck scale, where beyond that, our two best theories of how things behave in the universe, quantum mechanics and general relativity, give us different predictions. So we get two predictions for one scenario, so that's no good. So we sort of draw a line there and say, well, you know, we'd need a different theory out there. But of that range, you're looking at like maximum one part in 10 to the 90. So a number with 90-ish digits in it turns up on the bottom of the probabilities here. So that's a case where there's various things that sort of hem various reasons why it's a very solid case, just because it's you know, it's such a clear case of, oh, you know, if you get this number wrong, you're finished. And it seems like there's a whole bunch of ways that we could generate the sort of universe, at least in our models, that would blow up like that. And there's various ways in which future physics won't necessarily help us out. It's, you know, it's a problem in physics as we understand it. So that's one case. Another one, very briefly, is really sort of three. Once you start looking at the way our fundamental pieces are sort of put together. So if you break yourself, or you know, a pen or whatever, apart into the smallest bits, you find the electron, that thing going around the outside of atoms, and the stuff that protons and neutrons are made of, up quarks and down quarks. And if you then take a three-dimensional sort of space to represent the possibilities for those three numbers and start messing around with those and going in this way and that way and seeing what would have happened in the equations if those numbers had been different, you get a very small bit of the total space that allows, you know, anything to stick to anything else. So large bits of that space are ruled out by, for example, there's parts where, you know, you think about a way an atom's put together. You've got protons and neutrons stuck together in a nucleus. For an awful lot of the whole of the parameter space, the set of possibilities, either a proton within a nucleus will decay, so that nucleus is gone, or the neutron in the nucleus will decay, so that nucleus is gone. And so you just very easily erase the entire periodic table. There's just no way to put anything together. You have a universe which is pure hydrogen or pure neutrons. It's just, and you can't make structure out of that.
Yeah. One other example that Aaron Wall suggested was one of the ones he finds most impressive is the Higgs mass, where he thinks that he thinks this one's particularly impressive because, like the cosmological constant, it's harder to solve it with deeper physics because in both cases, like the value of the Higgs mass that it needs to be is affected by other values in physics. And so long as you think that what's happening at the micro scale isn't affected by what's happening at the macro scale, then it's improbable that the micro scale stuff would be set to just the right level to get the right Higgs mass and to get the right cosmological constant. I guess, you know, I don't understand the physics. You know, I'm just a philosophy student. Do you also find the Higgs mass fine tuning to be similarly impressive?
That's sort of related to the one I just said with the Higgs. So it's the Higgs vacuum expectation value. Aaron knows more about this than I do, but so basically, actually, I said there's three numbers. A better way to think about it is actually there's kind of four numbers where there's an overall scale, the Higgs vacuum expectation value, which says all your masses are roughly here. And then there's three more numbers for each of those three particles, which is where you are relative to that overall scale. And so the overall scale is the one you've really got to nail. You've also got to get the relative ones right. So there's sort of 4 cases, but one very impressive one, which is the overall scale, the Higgs vacuum expectation value. And yeah, he's right. One of the things that's particularly impressive about the masses, or the Higgs, however you want to do it, is it's not the case that there's a nice, easy, natural number waiting for you. Like if you just hit 0, you're all right. Or if you just hit 1, you're okay. The number you've got to hit in the appropriate units is something times 10 to the minus 17, where there's no how would a universe know to hit that, right? Suddenly you get in that range and bam, the periodic table turns up, and the whole, in our universe, you can go to on your browser PubChem, which is a database of chemistry, and there's 119 million known chemical compounds, and that only happens in this tiny little weird corner of parameter space where here we are. But change these numbers and they're all gone. All the other elements, all the other elements are gone, let alone all those other 119 million compounds.
Yeah, so I guess with say the cosmological constant, like if it were set to 0, would that be life permitting, or does it have to be set in this really small value, but this value that remains somewhat, remains positive?
Yeah, so that's interesting. So 0 is fine, which for a while made us think, oh, maybe before we knew the cosmological constant isn't 0, we were sort of thinking, oh, well, if maybe one of the solutions to how did the universe get just the right cosmological constant is maybe for some reason, for some symmetry reason or whatever, it just is 0, which is why in 1998, when we found out it's not 0, that's quite the problem, because you can't say, oh, it has to be 0 when it isn't, in fact, 0. So suddenly all those symmetries that could have solved the fine-tuning problem, they're all out the window because they're not true, right? They don't hold in our universe. So they can't solve fine-tuning if they don't even hold for us. They can't tell every possible universe, no, you can't have a non-zero cosmological constant, when they can't even tell our universe not to have a non-zero cosmological constant.
Right. Yeah. So maybe an analogy would be like, like given that there are all these different values that go into it, it would be sort of like if you took Bill Gates' annual expenditure and then you subtracted, 1% of the GDP of Micronesia. And then once you do this, there are 5 cents left over. It's very improbable that it would be that small. Now, if it were exactly 0, then maybe you could say, well, maybe, I don't know, Bill Gates runs the economy of Micronesia or something. So you could have some explanation. But if it's small but positive, then it's harder to do that. I guess and maybe that this just wouldn't work at all for complicated physics reasons that I don't understand. But what about having a sort of intermediate position where the symmetries are such that like most of the things cancel out, but remains a small positive remnant that results in a positive cosmological constant?
Yes, supersymmetry is supposed to do that. And so there's 2 issues there. One of them is there's still, into the models, you have to make sure you get the number that, like, what the equivalent of your 5 cents, right? There's a number that you have to get that left. What's the leftover in your model, I suppose? Because if you need it to be 5 cents, and it consistently gives you $1, that's no good, right? So the other major problem with supersymmetry is it should have, in its simplest forms, probably should have shown up already in particle accelerators like the LHC, but so far we haven't seen anything. But yeah.
Yeah. Right. Okay. So I understand. So maybe there are these technical physics problems with supersymmetry specifically, which is, I think, one way of doing it. But what would you think about, like, thinking, maybe there's going to be some unknown explanation that's going to involve invoking more advanced physics that'll have some other way to roughly cancel out the symmetries?
Yeah. So the problem is it starts getting all a bit. Well, two things. I think the whole idea of the fine-tuning sort of scenario entirely is we're taking stock of where we are. Right? If better physics turns up tomorrow, we'll have a look at that and we'll see what its parameters are. And we'll start messing with those parameters and we'll do all this again. That's fine. So the argument's not claiming to be completely future-proof, but I think it's still very interesting if where we are in physics right now sort of backs up the design argument, because it backs it up the whole way, right? If you think, you see, the amazing universe. There's a parrot literally right there. It's welcome to Australia. If you see amazing things out in the world, and you think, this is extraordinary, but then someone says, the natural world can build those parrots given enough time and the laws of nature. But then you see all the way down. It takes remarkable coincidences all the way down to the bottom of the best physics we know about to have a universe in which it's possible to build a parrot. Then you've still got a reason to take the design you see in the natural world very seriously. But it's, if tomorrow everything changes, then we'll deal with that. I think Aaron Wall is particularly good on why the cosmological constant is particularly future-proof. One of the reasons is if there was new physics, it should show up at some point, right? If you're going to say there's new physics for this reason or that reason. So if you want to say there's new physics about how particles, how the fields in our universe, how they interact with each other, that should make a difference at some point. And the point of the cosmological constant is you can't say that all of that difference is going to happen way up at very high energies in scenarios we haven't reached yet, because the problem is sort of there the whole way down, which is why the failure of us finding supersymmetry really is that sort of problem, that, we needed the stuff of our universe to behave differently to the way we think it does in order to solve the cosmological constant problem. And we're now at scales where, look, we haven't seen anything here yet, so nothing's come along to save us, and we needed something to have saved us by now, so to speak. In our sort of, by now meaning on our sort of journey upwards in energy as we go to higher and higher energies to try and work out what happens to the stuff of the universe as you throw it around.
Right. Yeah. So I think, yeah, right. So the problem with the deeper physics explanation is that you'd have to have this stuff at the small scales, all these little things canceling out. So then it's sort of like, then you need fine tuning for all the things to roughly cancel out. But so that was why I was proposing the explanation where you think the stuff at small scales, almost all the stuff at small scales cancels out, but then you just have like a few things left over. I agree that, this is going to be a bit ad hoc, I think, but, we should have, so, we shouldn't hold out, it certainly will mean that the fine tuning argument carries some significant evidence. But is there any sort of thing that in principle would rule out this kind of scenario where almost everything cancels out, but then there's just a little bit left over, and so zero wouldn't be zero would, if it were at zero, you would hold out hope, maybe for if the cosmological constant were zero, you could hold out hope for saying, look, the values that are affecting the cosmological constant, the other things in physics, the things that explain the positive values also explain equal and negative values. And so that's why it's zero. But you might think, well, this holds for almost everything, except there's a little bit that's not canceled out. And so that's why it's only slightly positive.
So certainly we can't rule out things in general. I don't think we're up against that. Sometimes, physics gets very powerful sort of no-go theorems and that sort of thing. But I don't think we're in the range of any of those here. Here's one of the reasons why there's reason to be skeptical of that. So part of the problem, the cosmological constant problem, is that we have these things, quantum fields. So the electron is really a quantum field. The up quark, the down quark, they're all fields, which means that what you can think of a field as just like a magnetic field. It's just kind of everywhere. And then a particle is just a very particular way to send a ripple through the field. Then the question is, if there's energy in the field, even when there's no particle rippling through it, then it will act like a cosmological constant. And the question now is, okay, all right, you have some idea about these fields. You have some idea about how much energy might be there rippling through the field. When it's the energy in the field when it's not there, the vacuum state. How seriously can we take this? And the answer is, well, there are scenarios in quantum field theory where we need to take into account these vacuum properties. The field is still there even when there's no electron around, in making predictions that are testable. Something called the Lamb shift. So if you take into account the fact that the field is still there even when a particle isn't, and you take that into account when you calculate the property of a particular electron doing a particular thing, and lo and behold, if you take that into account, you get the right answer. So you have to find a way to mess with your physics on scales where we've tested it to via things like testing the Lamb shift, your understanding of how the field behaves even when there's not a particle there. Again, you don't have complete freedom. So to do whatever you like, because right, you can mess around with scenarios and where we've actually tested what's going on. So it is. Look, it's all I'll say is there's a lot of hoops to jump through.
Yeah,
maybe it can be done, but it's not straightforward to say, oh, this is going to cancel and that's going to cancel. That was sort of the magic of supersymmetry, but even that lands you now at too high an energy, blah blah blah. So yeah, there's a lot of hoops to go through.
Yeah, that makes sense. And then at some point, if you have the thing go through all the hoops, then it starts to look like you need fine tuning to have the thing go through the right hoops. Where then you need to finely tune it to have the stuff at the deepest level be set so that it sets the higher values for the constants. Like this is a point that Robin Collins has made, where then you need, if you get 10 royal flushes in poker, even though that's obviously going to be fixed by deeper physics, no one would say, well, deeper physics means that that's not evidence for the cheating hypothesis because it's by deeper physics. Because the deeper physics is much more likely. It's much more likely that there will be some kind of deeper physics on which you get 10 royal flushes on account of you cheating than on account of you not cheating. Right. So regarding other explanations so a more general question about fine tuning, like roughly how many kinds of fine tuning are there? Like, do you think there are that are pretty impressive? Like, there are lots of people who, I was reading one of your blog posts where you were criticizing Eric Metaxas, where he was, I think, just, throwing out random fine tuning numbers that weren't serious. But, is it on the order of like 3 or is it on the order of like 10 or could be more or fewer?
So there seems to be this thing where I see in some writers, Metaxas one of them, where when you describe a case of fine tuning, just say whatever you like and then say the number 10 to the power of 100 and that's fine tuning. It's like, oh, come on, man. We work hard on this thing. So how many cases are there? So cosmological constant, as I said, the case of the masses is kind of 4. One, the overall scale of the masses of the fundamental particles, and then they're called the Yukawa couplings, the masses those relative to that scale. I think there's probably at least one other quark mass that needs to be fine-tuned, although that's at some point things get a bit like, I suspect fine-tuning, but I'm not entirely sure. I suspect the strange quark mass does need to be fine-tuned. But we can leave that off for now. I think the strengths of the forces. So there are numbers that represent, say, how strong is electromagnetism, how strong is the strong nuclear force, how strong is the weak nuclear force. I think those need to be fine-tuned. However, I think once you get down to the nitty-gritty of those, it's probably percent level. So 1 part in 100 kind of level fine-tunings. which would be interesting and worth looking at, but we're not sort of 10 to the 90 scale things. There's things like, I mean, in our universe, neutrinos have a very small mass, but we're not entirely sure what the mechanism for that is, how neutrinos have mass. There's ideas, but we're just not sure which one's right. But we know that if they were too heavy, they would affect the way structure forms in our universe. But it's just a bit hard without knowing exactly which model to look at. It's hard to know what number to put on that. So again, I suspect fine tuning. It's something you've got to get right, but I don't know how to turn that into just a straight up probability. And then, yeah, there's a few other cases. So the initial lumpiness of the universe, so to speak, the scalar fluctuation amplitude. So in our universe in its earlier stages isn't perfectly smooth. So if you took a sort of random bit of the universe and measured its density, so just go around and get a bucket of stuff and see how much matter you pick up in your bucket in the universe, those numbers will match to the first 5 decimal places, but be different after that. So there'll be a 1 in 100,000-ish difference in density from here to there, right, in different bits of the universe. And that's enough that then the densest bits, gravity says, well, there's a bit more matter here, so I'll start drawing in stuff from everywhere else, and the stuff that's underdense hasn't got the same pull. This is how structure forms in our universe. But that number of 1 in 10 to the 5, 1 in 100,000, if you get that number wrong, if it's too small, you probably won't make structure at all. If it's too big, this is where things get a little bit hairy. There used to be what we thought was a hard limit where if you're beyond that, things will be a bit dense. And then some interesting work by Fred Adams pointed out that, well, if the center of galaxies is too dense, you just live a bit further out, which is kind of what you have to do in our universe anyway. But if you made that number too big, you'd probably make a universe full of black holes if it was way bigger. But again, it's a bit hard to put a number on that. So there's a bunch of cases that sort of around the edge where you would have to work fairly hard to justify a probability over a certain range. But I think the solid cases, the ones I talked about, there's ways to do that, which is why I tend to focus on those sorts of cases.
Okay, so it's like cosmological. So the really solid ones are like cosmological constant, the Yukawa couplings, where there are 3 of those, and then the kind of like Higgs mass, where the mass. Okay. All right, makes it so. So in your book, I think it's called The Fortunate Universe. Sorry, is it?
Yes, The Fortunate Universe.
Oh, fortunate. Oh, okay, sorry. So I think your co-author thinks that the best explanation is the multiverse. That's the best way to explain fine-tuning. So, I mean, I guess the first question would be, do you agree that if you're an atheist, you should go for a multiverse to explain fine-tuning? And then second, what's wrong with the multiverse explanation?
What would I do if I was an atheist? Yeah, I think I probably would go for the multiverse, to be perfectly honest. Either that or take a very hard line on, like, if I just ramp up the what I need to think that I really have some probabilities, if I just make it so that I take what I actually think is an unreasonably strict account of that. But if I won't allow probabilities, any talk of probabilities except in extremely specific circumstances, I could try and rule things out that way as well. Some people have tried that. But the multiverse,
like by sort of like being like a frequentist or something in the vicinity, where I guess I think to me a multiverse seems like a much better way to go if you're an atheist, because I think if you're a frequentist, then you literally can't even say things like evolution is probable.
Yeah, exactly.
Where like most of the evidence for evolution is just really surprising patterns that are highly expected given evolution and very unexpected given the falsity of evolution, like nested hierarchies, and this molecular evidence where we can trace the common lineage. But if it's not like we've done evolution, we've had the life from we've done common descent 30 times in a lab, and it usually turns out one way. And so I think there you're just in complete skepticism. about like most probabilities, or you can't say things like, probably such and such candidate will win the election. Where,
But I have seen people. So I was at a fine tuning workshop about a year and a half ago, and there's very simple scenarios of I offer you two paper bags, right? And in one of them there's 100 envelopes, and in one of those envelopes there's $50, and in the other one there's 2 envelopes, and in one of those envelopes is $50. Wouldn't you just say, isn't the right way to analyze that to say, look, there's a 1 in 100 chance of getting $50 in this envelope, in this bag, and a 1 in 2 chance of getting the $50 in this bag, even though you don't know anything else? Like, can't I just reason about the world that way? And there's this hard line of if you're dealing with probabilities are only very restricted to the way our universe is and the experience we have, and they're sort of connected to fundamental, probabilities that we need to explain things in physics. But this idea of using them above physics, over physics, if you draw a hard line there, then you can, shut down the fine-tuning argument before it starts, I suppose.
Yeah, I do think one problem there is you might actually just get the result that like much of what we're doing in physics is silly, where if you don't think that there's anything virtuous, theoretically virtuous, about explaining why the values in physics take on physicists are trying to explain why things take on the values that they do in terms of deeper stuff. And if you think, well, we don't even need to do that because we can just invoke that it takes on such and such value, and you can't even say that's improbable because we have a sample size of 1, then it would throw much of physics just into disarray.
Yeah, again, I don't think you can you can't sort of phone this in half and half, but the people who I'm thinking of here are Humeans, right? So they follow the sort of modern version of David Hume, where the idea is, it starts from a picture of, I'm going to try and get in their mindset. It starts from a picture of what a scientific law is. So it basically, there is the Humean mosaic, which is all the events that happen in the universe over all of time. So imagine you just had this big database, which is where everything in the universe was and how it was moving, where all the electrons are and where all the protons are, all that sort of stuff. If you just got this ridiculous amount of detail on this one database in front of you. Well, what is a law of nature? Well, according to the Humeans, a law of nature comes after that. And it says, look, here's a nice way to summarize some of this. And that's all. And once you've done some work working through this colossal database, the best system of summarizing the data just is our statement as a part of that best system just is a law of nature. So that's the way you do it. And if you're doing that, then probabilities can be part of that best system, because sometimes it's just easier to assume things are evenly distributed or randomly distributed or pseudo randomly distributed or whatever. So that's all fine, but that's all happening. Like, the universe just is, it's just there, and we're trying to describe it. So all of this, what about other universes? What about other possibilities? You just sort of rule that out as, what's Hume's, if it's not observable, throw it in the fire. He said it better than that, but it's that sort of idea.
Yeah. I mean, I do think that will have, that will have certain problems of just throwing sort of normal probabilistic reasoning into disarray, where it'll imply that if there's one theory that has just a bunch of parameters set to really, really arbitrary values, and there's some other theory that just explains perfectly why they all have those values, then the second theory won't be favored over the first theory, right? Because it's just in terms of coming up with a regularity. Where even if you think that these are just sort of law, where it's just basically the Humean picture is stuff happens and laws are these nice descriptions of basically what's happening, where the stuff happening is what has primacy. Well, it's still improbable that stuff would happen in accordance with the cosmological constant set to this very small range. But okay, so regarding a multiverse, So what do you make of the multiverse explanation of fine tuning?
So there's an interesting debate about whether it's really science. So you can find some very senior, very well-respected cosmologists, George Ellis and Joe Silk. There's an article they wrote about 10 years ago now. It was in Nature, basically saying, look, we're scientists. What are we doing? Like, what is this? We're supposed to be, empirical and hard-headed and all that sort of stuff. But what is this? What is this garbage? Why on earth are you talking about other universes we almost certainly couldn't possibly observe? There's that line. I don't take that sort of hard line. I think that problem sort of comes back, but I think there is something a multiverse model could do, which is to explain the values of the constants, which is at the moment unexplained. My major problem with the multiverse is that even the best scenarios we have at the moment for that are really toy models where most of the physics goes in by hand. And it's for a lot of them, it's very hard to get a prediction out at all, let alone to know it's the right prediction, because there's infinities lurking around, which often, if you don't control them right, make a mockery out of any attempt to do probabilities. But if you do control them, the way we control infinities, so to speak, we can handle infinities in mathematics, but you end up having things like two identical copies of me and Earth and all that sort of. They don't end up counting for the same amount of observer, depending on how you start adding up all the infinite bits of the universe. Just as a very simple way to show that there's a problem. If you want to say, look, I think I'm here on a planet surrounded by, a house and trees and all that sort of stuff. Is it really the case that that's true, or are my eyes just playing a trick on me? Well, you'd like it to be the case. If you knew all of physics, you could say something like, well, most of the people who think they're on a planet surrounded by a house and some trees really are on a planet with a house and some trees around them. And then you start to think, well, actually, there is a chance that you could physically have a system, a brain, which is in this state that I'm in now, but without the house and the trees. I'm having a hallucination, a complete hallucination. I'm just a brain in the middle of nowhere that just popped out of nothing, and I'm having an experience of being in a house with some trees. And what you need in order for your model of the universe to make sense and not to just go down some skeptical rabbit hole where you'll never come out again, is to say, well, look, most of the observers, almost all of them, hopefully, if they're in this brain state, it's because they really are in a house with trees. And so we can rely on our own faculties. But if there's infinities hanging around, you're in a bit of a problem, because there could be an infinite number of these brain states out there. And now you try and get to the most or almost all conclusion where you say how many of them are in the I'm really in a room situation, and how many of them are in this weird brain just popped out of nowhere situation. And if the answer to both of those is an infinite number, well, what do you do next? You can't just do infinity divided by infinity. So now you've got to start to try and control your infinities. And you might try and do it by volume or by, you need some sort of method, and there's competing methods. This is called the measure problem, and it's not straightforward. So I find the current state of multiverse models to be a bit primitive because we're sort of guessing in the dark. The other thing I'd say is, if I'm thinking of them, I'm starting to think of the fine-tuning model, not fine-tuning argument, not as sort of an independent thing, but as sort of backup for our sort of primary experience of nature as being this place looks well put together. It's sort of a design intuition, right? And the problem is that design intuition for the last 100 and whatever years, 50, 60 years, we got told, oh no, Darwin explains why your intuitions of design are actually wrong, because the natural world can put together the things that you think are designed by God. And what fine-tuning does is says, sure, right? If the evidence points to evolution, we can go with that. But right, that doesn't mean that all the design is gone. It just means that you have. I think there's a quote from an old. I forget who said this, but it's designed by wholesale rather than designed by retail. It's designed down in the factory rather than just in the product. It's designed in the mechanism, which then makes the design all the way up. So what it does is it sort of it returns you back to your intuition rather than being a separate argument. So the problem with the multiverse is just, we followed design all the way down. And what the multiverse says is, okay, what if I imagine a deeper mechanism that might make it look less designed? And the answer is, well, I can imagine deeper mechanisms which are designed. So what do we do? There's no evidence here. You just imagined a scenario. And the problem is design sort of followed us all the way down. So why not think it just follows us all the way to the bottom? So the problem with the multiverse is we're trying to take the best stock we can of physics as it is at the moment. And the multiverse isn't the best physics we have at the moment. So why should I care what you can imagine?
Right. So I think so. A proponent of the multiverse. So I agree. I think the measure problem is definitely a big problem for multiverse models. Because generally, if you have some universe generating process, well, by default it'll run forever, and then you'll get infinite on both sides. But also generally the way that people will try to take a measure is it'll be some way where they'll look at the density of observers in regions of space-time or something. But the problem is if you have an infinite set, you can change around the density just by moving people around. And so most of these will imply that just by shifting people around, you won't that you would just change the measure. So all the people some people have red shirts, some people have blue shirts. You think with probability 0.6 that you have a red shirt, and then all the people move around, and now you think with probability 0.3 you have a blue shirt, even though it didn't change whether any of the people had a red shirt or a blue shirt. And that's a big problem. Actually, maybe this is too much of a digression, but I think there might be an argument for God in this vicinity, where if you think that if you conclude that there are infinite people, it seems like by default this leads to skepticism because just there are infinite people with every property. But if you have a God who for every particular person makes them undergo some process that every particular person who's being created makes them undergo some process that mostly places them in scenarios of a certain sort, then you can still get the probabilities to be high that you'll have particular properties. So for example, if you're in Hilbert's Hotel and you all roll dice, the same number of people will get 1 through 5 as will get 6. But nonetheless, you should think with 5/6 probability that you'll get 1 through 5. Yeah. So you might think God does something like that, and then that saves us from the probabilities not working out. But okay, that's a bit of a digression.
I don't think it is. I think that's quite relevant because it is. But that's the measure problem, right? So the paper by Ken Olum, OLUM, presenting these sorts of arguments, but in the physics literature, if you want to go and look that up. I think it's from 2012. But it's exactly the sort of problem here. You can't, if the way, it's not that as physicists and mathematicians, you can't handle infinity, just the ways you do it. If you translate that into what you're really thinking about the model, you end up doing that exactly what you said about, you moved the red and blue shirts around and suddenly the probabilities change. Like what? It's exactly that sort of problem.
So and it's even a problem if there's just a single infinite universe that's just infinite in size, because by moving the people around you could change the density in any which way. But so I certainly think the measure problem is a big problem, and it's not super obvious what to say. And I actually think probably there can't. It's not just we don't know exactly what to say. I think there probably can't be a thing to say, because any solution will look at the pattern of how the observers are distributed. But if it's infinite, if there are infinite people, given that it's infinite sets of the same cardinality, just by moving the people around, you can change the way they're distributed. So it'll inevitably imply that your probability function is sympathetic to where the people are located. So I think that's a big problem. But so regarding the multiverse, so the other objection that you raised, and I've heard you raise this in various places, is you say, look, it's based on the fine-tuning argument is based on our deepest physics. And the multiverse right now, we don't really have well worked out multiverse models. At this point, they're basically a promissory note where, it hasn't been worked out. But I mean, imagine you could make a similar, like imagine prior to, imagine say, prior to Darwin, where a person says, look, maybe there's some deeper explanation of this biological life. And in response, a person says, well, at this point, pre-Darwin, all our theories of this are just promissory notes. None of them are well worked out. It seems perfectly reasonable in that case to say, well, yeah, we don't have a worked out theory of it, but it's not that unlikely that someone will come along and come up with a well worked out theory that turns out to be correct. So why not think, look, we don't have multiverse models that solve all the problems yet, but maybe we'll get some eventually.
Yeah, so there's a really interesting case here, which is you like to do that specifically for William Paley. So the sort of famous design argument before Darwin, where he does talk through a lot of scenarios of how life could have formed, naturally. And he's sort of almost there for evolution, but not quite. It's quite interesting, and I need to read that section again. Whatever the natural, what's it called? Natural theology. So that's a really interesting point. I think the important thing is not whether there is a deeper explanation, but whether when that deeper explanation comes, it will be the kind of explanation that does away with our design inference, our design intuition of the world. And I think that point's been glossed over. So it's right. I can see it right there behind me. There it is. There's The Blind Watchmaker by Richard Dawkins. He says, I think it's the first page. Biology is the study of things that look that look designed for a purpose, and physics is the study of simple things that don't tempt us to invoke design. So, if you say, pre-Darwin, you say, well, there could be a physical mechanism we don't understand yet that could assemble living things. And the question is not entirely whether that's true, although that's obviously very relevant, but that's not enough. It needs to be the kind of mechanism of which it's plausible to say, and this mechanism doesn't tempt us to invoke design. Because you can think about Dawkins' state of mind, right? He's thinking, oh, it's just atoms and chemicals and molecules, and they don't look designed. So hey presto, we've done it. We've taken the natural world. I've taken the parrot, and I've produced a physical process which will make the parrot, and everything looks nice and simple down at the lower level. Whereas what you really should be asking is, okay, when this new mechanism comes along, will it itself look designed? And you have to ask that question the right way. So Dawkins just kind of looks at physics and goes, well, that's way simpler than biology, right? There's only 92 naturally occurring elements as opposed to all the forms of life. And all those naturally occurring chemical elements can be made out of protons and neutrons and electrons. And, right, that looks nice and simple. Whereas we eventually worked out that the right question to ask was the fine-tuning question. What if I change these constants? So it's not, there's two separate questions here, and the question of whether there is a true explanation isn't enough. It's also got to be the kind of explanation that doesn't make us suspect design. So again, when a multiverse explanation turns up, yeah, maybe there is one, and there's certainly sort of half ideas out there. The deeper question is going to be: does it itself look designed?
Yeah. And so, sorry, briefly, roughly how much longer should we go for?
If what are we at? 10 minutes away from an hour, like another 10 minutes. I'd have to get to work at some point. But
right, sounds good. Yeah. Right. So there's a question. Right? Will design show up at the deepest level? And your thought is, look, design shows up at a level, then we explain it in terms of deeper stuff, and then we see actually that deeper stuff also requires design, and then we explain that in terms of deeper stuff. And so your inductive, and so the inductive trend that you draw from that is probably the stuff at the deepest levels is going to look for design. So I have kind of two worries about this. One of them is that it's not like we have this very long inductive pattern of like, there are 10,000 things, each of them we've explained in terms of deeper stuff. Like really, it's just basically like there was a natural world and it looked designed, and then we explained it in terms of the behavior of cellular replicators, and then when we investigate these at the deepest level for fine-tuning reasons, it looks designed. But so it's hard, you don't want to, it's hard to like be super confident in an inductive trend that's basically extrapolated from roughly 2 data points. And second, maybe you could also explain the inductive trend by saying, look, all the stuff, once we explain the stuff, then the design goes away. Then the need for design goes away, right? So with say, biological life, before we had a deeper explanation of it, then it looked designed. Once we explain it, then it no longer looks designed. And so then on that, you would expect the same inductive trend of all the stuff up until the deepest level looks designed. But at the deepest level, the stuff would look not designed. And then it's not obvious which inductive trend to privilege between the design goes all the way down and design goes down. Like stuff looks designed often, stuff only looks at designed when we haven't yet explained it. And so then design goes down to all but the deepest level. So I guess, I'd be curious to hear what you'd make of that.
So for me, I think we've been living in the story that Dawkins tried to tell, right? With Bertrand Russell tried to tell. Like it turned out, was that quote from Russell? We're all accidental collocations of atom. There's physics. And that's all just mindless stuff bouncing around. And look, thanks to, the processes that Darwin discovered, it might accidentally throw itself together into some people. Not randomly, of course. Dawkins is very clear about that. But it all happened accidentally and blind and all that sort of stuff. And fine-tuning just, I think it really does stick a knife in that. Like it, if something looks designed, but then it's actually the product of a mechanism, then you have a good reason to think that the mechanism is designed. You could take design on a very broad, back design off to a very basic thing like, if actually Dawkins does this quite well. If a thing looks like it has a very particular arrangement amongst the set of all arrangements that does something functional, right? Then, that level of design, Dawkins says, if you take the cells of a bird and you throw cells together at random for 1 billion years, it'll never fly. That sort of thing. Well, we discovered if you throw a universe together for 1 billion years, it won't fly either. So, that on that level, I think you've got to then start to think, well, what would it look like if the universe was actually designed? And the answer would be there would be some outcome that the designer wanted, in this case, amongst other outcomes, at least they wanted embodied life in our universe, embodied moral agents, let's say. Well, if they wanted that, but they didn't want to just create that, in a second, they'd build it up from deeper levels of predictable stuff to give it an environment to live in. In that case, the sort of trend that we see is what you would expect, that, you don't get that sort of life for free. So, you would expect the design to start following you all the way down, however you think about it. So I think when we thought that the existence of a deeper level of explanation sort of erased design is because we were asking the wrong question. We only asked whether Darwin is true. We didn't ask whether Darwin itself, that mechanism, requires more design underneath it. And once we started to ask that question, sort of accidentally asking the right question in fine-tuning, that the real answer came out. But that's an interesting point, actually. I probably need a better answer.
Yeah, so I guess one other worry with this analogy is that, so I could see how you could be maybe confident in the inductive trend if, like, okay, imagine it was, so we explain Darwinian mechanisms, we explain the diversity of life in terms of these Darwinian mechanisms, basically in terms of the natural result of these cellular replicators. Now, suppose it had turned out that the cellular replicators, that's where it looked like, the real money was on design. Well, then, and then you go a deeper layer than that, and you say that looks like it requires design. Okay, that would be fairly impressive, or at some point, barring my other words, maybe it would be reasonable to say that there's an inductive trend. But I mean, it's possible you disagree, but I don't think that the impressive looking kind of design is in the cellular replicator. It's much deeper at a layer of physics. So it's not like, well, we explain this design in terms of this other thing, but then this looks designed. It's we explain this thing that looks designed in terms of this other thing, and then 10 layers deeper that requires design. And so then it becomes less clear that, like, design always, the stuff that looks designed always is explained in terms of stuff that itself looks designed. It's just that, like, you might think that the broader trend is just, look, we've discovered a few examples of things that are designed. One of the things that we've discovered that looked designed for a while, we've now discovered a mechanism. Now, then when we explored a different area, we discovered that other area was designed, but maybe there we'll discover another mechanism. Now, I have doubts about that for the reason, for the some of the reasons we talked about for why the deeper physics explanation won't be adequate. But I kind of think, like, I'm not too persuaded by this sort of inductive point about, like, well, the deeper you go, the more you find design. When it seems like we're drawing a line through two data points where and then it's just like when there are other ways to draw the inductive extrapolation, and the inductive extrapolation is, it's not like the thing that we discover that explains the design itself needed design. It instead needed design at, like, a much deeper layer.
So let me try and throw a few extra points in there. Although I mean, if you have a problem with an induction with only 2 points, adding an extra 2 is not going to convince you. But in terms of the replicator, there was a time in the history of biology where the cell itself was referred to as a blob of protoplasm. Right. And you can see what's happening there. Like, the parrot is an amazing thing, but don't worry, it's built up of these little blobs, and they're pretty simple things. And so at that level, we could say, right, what Dawkins is saying, like, the sort of simplicity that doesn't tempt us to invoke design. And it was the hope that maybe the cell will be that simple. And then we looked more closely at the cell, and it's incredible, right? It's got its own postal system, right? That literally molecules have worked out their own postal system. They put a little address, they have little highways and postal workers and trucks, and all of that's happening with molecules, like, phenomenal. And so, right, and so the blob of protoplasm became one of the most amazing micro mechanisms we've ever seen and will ever see. Oh, all right, let's go a level D. Maybe chemicals are the simple thing. And then there are voices like Henderson. There's a very interesting, it's a sort of pre-fine-tuning days. In 1913, there's a very interesting book by, I think his first name's Lawrence, but Henderson, The Fitness of the Environment, pointing out that, there are some very unusual properties of things like water that most molecules don't have. And so it seems like you could have had a universe where no molecules had this property, but which life requires in very interesting and delicate ways. And then, suddenly the simplicity you're trying to find keeps evading you. So maybe that doesn't fully answer this sort of problem, but given this Dawkins style, I just need to find simplicity somewhere at the bottom. That's not been the right approach. It turns out to be the sort of, it's simplicity down at the level of physics in terms of elegant equations, but you've still got to get these constants right. There's still the sort of, you need the right mix of simplicity and complexity.
Right. Well, I mean, we wouldn't want to say that. I'm sorry. I'll let you go in a moment. But we wouldn't want to say that, like, the deepest level won't be simple. I think you and I as theists, we'd say the deepest level, it will be simple. It's this God, wholly without parts. And so we don't want to say that the inductive trend, like, means that the deepest layer won't be simple. Ultimately, we think it will be explained simply. And so then the question is just, exactly what will the deepest layer that is simple, what will it look like? But I don't know, there doesn't seem anything right. So
that's a great way to frame it. Just to say, what is the simplest thing going to look like if you're a theist? Well, it's a mind who could have purposes, who could then bring about more complicated things like a physical universe capable of supporting embodied life. What's the simplest sort of thing that might turn up on naturalism? Well, one type of particle bouncing around in a mostly empty universe. It's not alive. So that's a good way to actually get at the problem here, is that the reason why the naturalist wants simplicity, but wants simple matter, right? Matter, like the protoplasm blob, or just simple chemicals stuck together, or maybe just quarks, and it keeps turning out to be that the simplest option on naturalism won't make the universe we see around us. This just isn't the simplest one, and so the naturalist will never find that simple design obliterating simplicity that they wanted at some fundamental level. It's not there because you need a mind at the bottom.
Right, but if you agree that the inductive trend can't be just like like complex design begets more complex design the deeper you go, because we're all going to say that it bottoms out at some simple level.
Sure.
Well, then it's hard to see on what grounds you're going to say, well, the naturalist, they can't invoke something simple at the deepest level, like a multiverse, like a kind of simple multiverse to explain design, when you don't want to say the inductive trend goes all the way down, because then that would rule out God for being the simple explanation. And so if we are all going to agree that, look, at the deepest level, there's something that's simple that explains the rest of the stuff that looks designed, I guess I don't see what's wrong with the naturalist just saying, look, it seems like it's the multiverse that explains that.
Yeah, so I guess the question then is there a simple naturalistic universe that contains the stuff we see around us? And for me, it's just not obvious that exists at all. You just have to put some sort of complexity in at the bottom, right? So I think so. I should say that when are we allowed to step down a level? The sort of case I've been making is you need good, solid scientific reasons to say this level explains that level in a sort of mechanistic kind of way. Right, that's when you're allowed to step down. So we have life. Oh, it's made of cells. It's made of chemicals. It's made of quarks. That's when you're allowed to step through the levels. So it's like God isn't part of that sequence. There is a simplest level of nature. So I'm not relying on that induction to land on God at the bottom. I'm just saying,
yeah, okay. So
when do we go ask the question?
So the inductive trend is like the stuff in nature that looks designed gets explained by deeper stuff that itself looks designed, right? So then I guess so that's a good response. And then I guess the remaining worry would just be, well, why not think the inductive trend is the stuff that we haven't yet explained is the stuff that looks designed, and then when we explain it, then it stops looking designed, and so at the deepest level, then that stuff we wouldn't expect to be designed.
So the thing I would challenge there is when we explain it, it stops looking designed. I don't think that's true. Go look at a cell. Just go find it. Go to YouTube. Go find an animation of the way a cell works, and just stare at that for a while. Right? The impression of design doesn't leave us. Right? It was the promise of as Dawkins said of Darwin, that down deep enough that the impression of design will go. But he still says that biology is the study of things that look designed. Right? He's just hoping it goes away at some deeper level. But I mean, that's an interesting result, at least, that down at the bottom of the best physics we know, it's still there.
Yeah. I think that's a good point. There are more things to be said, but we've been going for roughly an hour, so it seems like a good stopping point. Luke, thanks so much for coming on. I think this has been quite an interesting conversation.
Some good points. All right, thanks very much.
All right, have a good one. Bye.
All right, I better